Hi everybody, this is Mr. Wright, and we're doing the weight of the car lab today. We're going to go out and push a car and see if we can figure out how much it weighs, how much force it takes to push it. Before you get there though, I want you to make sure you do those top 4 questions before you ever get to class. Then we'll go out and do number 5. We're going to push the car a distance of 30 meters. So everybody just write that down. We're going to be out at Brook and Breck and pushing the car. We're going to push it 3 times to get the average. Please don't write this down because I'm just going to make something up. And so let's just say we got an average of 40 seconds. That way I can use that number actually in a equation. Then it says to calculate the acceleration of the car. And remember that the average velocity is distance over time. Well, when we went into the lab and did the Newton's second law lab, we used an equation for acceleration that said that 2 times the distance over t squared was our acceleration. So what I'm going to do to get that acceleration of the car is I'm going to put 2 times the distance we went, which was 30, and divide that by my time, and I'm just going to put down 40 squared, 40 seconds here, and square that number. You only square the 40. Okay. And that's going to give me an answer here of 0.0375 meters per second squared. Now, the total force that we're going to push on these scales, we're going to try to get up to 100 pounds of force. So we're going to have 2 guys pushing on a bathroom scale with 100 pounds. But I also need to know the friction force because there's a certain amount of friction that acts against us. And let me just see if we can draw this. Let's see if this is your car here. This is our little car, and our little wheels there, and a little sombrero wheel. And we're pushing the car with 100 pounds this way. And it says we're going to push the car at a constant speed. Well, when we go out to do this lab, let's push the car at a constant speed. And when we push the car at a constant speed, let's say the scale is reading 70 pounds when it's going at a constant speed. Well, at a constant speed, that means the acceleration must be equal to 0. And if the acceleration is equal to 0, that means the total force, what we call the net force, has to equal 0. Well, if the net force equals 0, I'm going to get rid of this 100 because that's a little bit confusing there. If the net force is equal to 0, that means the 70 pounds going this way must be canceled by 70 pounds of friction. So there must be 70 pounds of friction going the opposite way. So the whole purpose of going out and pushing the car at a constant speed is to measure friction. And so I'm just going to put that down. Let's just say friction was 70 pounds. Well, if you're pushing with 100 pounds forward and friction pushes backwards with 70, we're going to take and we're going to say we have a total of 30 pounds of force actually going forward. So that's our net force on the car. On number 9, it says to calculate the experimental weight of the car, use the Newton's second law formula. Well, I want you to, I'm going to write it down here, guys. I want you to put yours there, but I'm going to write it down here so I have some more room. I want you to think about this. Remember last chapter when we said that time did not have a direction? Time in the x direction and time in the y direction were the same? Well, mass is the same way because mass is the amount of atoms in the car. So the mass in the x direction has to equal the mass in the y direction. Well, there was a formula triangle here that we said that acceleration was force over mass. And so if you cover up mass, just cover up that one right there, the formula is F over A. So what I'm going to do is I'm going to substitute in for M here. I'm going to substitute in F in the x direction divided by A in the x direction. And here I'm going to substitute in a force in the y direction over an acceleration in the y direction. Well, how in the heck does this give me the weight of the car? Well, doesn't weight act down? And since the force in the y direction is acting down, this is actually the weight of the car right here. And the acceleration downward due to weight is always 9.8. So this acceleration in the y direction is 9.8. This force that we have here is what we call the net force in the x direction, which we calculated to be 30 pounds. So I would put a 30 right up there. And then the acceleration in the x direction is how much acceleration we got when we pushed the car. And if you notice, that's up here at 0.0375. So I'm going to put in, for acceleration here, 0.0375. Let me rewrite this now so you can see what we have. So I'm going to have 30 pounds of force in the x direction divided by 0.0375 equals the force in the y direction, or the weight, divided by 9.8. Then you do the multiplication of Jesus. You cross multiply here. Well, if you cross multiply, that means that the force in the y direction times 0.0375 equals these two multiplied together, which is 30 times 9.8. You then divide both sides by 0.0375. 0.0375s will cancel out, and you're left with the weight of the car. And so that ends up being 7,840 pounds. I don't know why I was putting newtons there. Sorry about that. It's pounds. Well, now I want to compare this to the actual weight of the car. So when we get out there, I'm going to have you write down the actual weight of the car right there. Okay, we're going to compare the lab weight, this is our lab weight right here, to the actual weight. And when you do percent error, here's how you do percent error. Percent error is equal to the actual, that's going to be what I give you, it's going to be off the door of the car, minus the lab, which is going to be down here, okay? Put that parentheses around that and then divide that by the actual again, times 100. And we'll see how close we get. So that, once again, make sure you do 1 through 4 before you get here. And that's how you're going to do the weight of the car lab. Hope you have a great day. Bye. Oh, love you.